Thanks everyone. As mentioned, we'll be talking about architecting the next generation of carbon-aware compute and AI for edge infrastructure. So we'll be talking about concepts, system concepts, how this can be done. And we've done some of the work, so we'll talk about some of the aspects. My name is Uzair Qureshi. I'm joined with Manish. We both will be jointly presenting on this. So we will talk about some of the areas, some of the agenda topics, which is challenges and opportunities, use case and proof of concepts, what we have done, and then also potential sustainable architecture that we are looking. We like some collaboration from OCP, and then some prototyping work, and then call to action, how we all can participate as part of the sustainability work. So we'll go through the problem statements. So I think our challenges are huge. You can see the amount of presence up here at OCP. There's a huge amount of growth, both in edge to cloud. And there's, if you've seen the number of companies who have shown up with cooling and everything, so there's a huge impact that AI is basically driving a substantial amount of power increase. And then last but not least for the challenges are the climate implications. And those are specifically for telco and edge, where we would be deploying compute and AI more closer to the customers. So those are the challenges. In terms of inflection point, I think so the whole world is moving towards net zero. So that's becoming an inflection point and a business imperative for a lot of the countries in EU, for Asia, and even US, and driven by regulations. And then on top of that, we're seeing a visible appetite for companies looking for solutions that are basically able to manage energy and carbon at scale. And what we are proposing right now, it's again, it's a high-level proposal, is to provide a sustainable architecture that leverages global intelligence. We have a lot of data that we actually capture around temperature, weather conditions, and all this stuff. So we can leverage some of those stuff and then enable carbon and energy management. And then, and we'll talk about the space and time shifting also in future slides. So this is a high-level proposal. We'll dig a little bit deep on it. From the time we have, we'll probably be able to cover at least high level, and we can talk more after the discussion. So here's an example. Where our goal is all about how can we run a workload how can we have a workload where we consume the same proportion of energy. So the goal is basically if you run a workload, you should only consume that amount of energy, and then being able to bring the energy all the way down as when the workload is not being utilized. So we took an example of a traffic management usage. This is just an example to showcase what we are thinking in terms of that. So we took a traffic management usage where we looked at traffic incidents like accidents and all the stuff happening on the freeway. So we see a system utilization have a peaks and also the quiet times. So there are times where we're basically running at high compute and then running at the lower compute depending upon the traffic condition, weather conditions that we are dealing with. And we also, so there might be times where we saw a spikes. Manish was just talking about it. He drove from Folsom and took him 4.5 hours because there was a traffic incident. So if you take a traffic incident, you might have to spike the compute for a limited amount of time and till the safety incident, like an accident, is cleared, and then you can actually bring the compute back to the low utilization space. So the principle we are promoting up here is basically how can the workload should be proportional to the energy generated, and so that we have a better way of managing our carbon footprint. So like they say, across valleys and peaks and idle to full load. So we should be able to manage that depending upon what the needs of the workloads are. So here's a concept of time and space shifting. What is the time and space shifting? So here, what we basically, our intent is to make sure that we balance the application SLO, which is service level objectives, to basically based on the energy, the green energy that's available. So the goal is basically, if wherever the green energy is available, if you can move the workload based on the SLOs that is given, that's the concept of space shifting. So that means you take a workload. If you find a nearby location that has higher amount of green energy, you shift it to that location, and as long as the SLA or SLOs are met. So we can actually maximize the use of green energy, and once the green energy, and then that's the concept of space shifting. The time shifting is, you can either move it to another location, or you can schedule it at a different time where you have more green energy available, and that's a concept of time we are basically talking about up here. So the whole goal is, this is where the community efforts actually plays a huge role, where we have to look at some kind of intelligent workload scheduling algorithms to basically look at how to maximize the usage of energy, green energy, and reduce the carbon footprint for our infrastructure. And we're talking about edge, but I'm sure we can apply the same thing on the data center side also. So we'll go some of the concepts. So we talked about the space and time shifting and energy prioritization. Those are the two needs we basically believe that those are things we need to have in a system architecture to deliver this kind of concept. So what we did is, to prove our concept, we basically worked with a telco partner. So we basically said, you know what, let's actually prove what we are even talking about. So we took a 5G core workload, and we ran it, we basically profiled the workload for a whole 24 hours. We looked at the workload basically was running, you had some peak times, and then you had some quiet times during the course of the day. And what we realized is that a lot of the compute, like they're running at the same frequency and same core count while it's in a quiet time. So the goal was to see if it's not effective to use a system or a fleet at the same core frequency performance and core count, and the same core count when you are in quiet time. So which is extremely efficient way of reusing your resources. So we had a software implementation along with the silicon features we have in our silicon. We were able to optimize dynamically, actually, since it's a 5G core workload, we were able to dynamically adjust runtime power based on the network throughput. So what did we achieve out of it? So what we did achieve is we actually achieved about a 30% savings for a whole 24-hour period for a specific workload. Now, we also believed, we also been working with a lot of the cooling vendor companies for the edge, and we have one demo on the site right now at Intel's booth. We believe that with adding a cooling technology into the mix, we will be able to reduce this power substantially more. So 30 is just with software and the silicon features. When we looking at the cooling technologies, those energy savings could be substantially higher. So next, we'll talk about green aware with energy prioritization for edge. In this example, we took a video analytic. This is, again, working with the customer. We took a video analytic workload running at the roadside unit. So think of this as managing traffic or doing some kind of video analytic usages on an outdoor stuff, which was running on a green energy. What we did, our goal was basically how can we maximize the compute performance when you have the most green energy without wasting any green energy. So what we did is we ran the compute. The compute was run at a higher performance when we had systems with green energy. When there was no green energy or less green energy available, we were able to bring the performance down to an acceptable level. So the graph, the second graph we're talking about, when we have green energy, we're running at a much higher best performance. And then when we don't have green energy and we go back to the traditional sources, we reduce the power to an accelerated, to an acceptable SLA, which is still meeting the SLA was bare minimum. So in this way, we were able to showcase that by just prioritization of this energy, there was quite a bit saving for carbon emission as part of this effort. So next, I'll actually hand it off to Manish, who will actually talk about some of the sustainable architecture and prototyping work that we have done. Thanks, Manish.
Okay, thanks, yeah. Thanks, Uzair. So just to cover what I'm going to cover in the next few minutes is, Uzair explained the needs, the type of algorithms you can use to optimize, and so on and so forth, and then some examples of what we have done in the POC. So we step back and think of it as an architecture. So I'll go through that architecture, system architecture. It's no surprise, right? System architecture, not just hardware, software tooling. And then I'll go through the API. Again, we don't have time to actually go through here's the API we use or we're proposing, but that's the main sort of one of the things that I'm bringing here. And then finally, we'll go through a prototype design. If we have time, we'll show some example of the POC we did with that architecture, okay? Okay, so start with the whole system picture. Now this, I want to say that even though it looks like a single system, it's technically, we're talking about distributed systems. So again, our talk is mostly on the edge. It applies to cloud too, but we are talking about distributed systems. So the first thing is, you have to think of it as a, overall, even though this picture might look like a single system, it's like a distributed. And it will be clear when I cover the prototype. Okay, so let's start from the top. So we're talking about the orchestration layer. So in the orchestration layer, again, this is nothing new. We're not building something for making it sustainable. We're talking about where the touch points and what we have done. So on the top level, when you have a distributed systems, you will have like a fleet. So let's call it a fleet management system, right? The fleet management system is responsible for doing all the things that you normally do, security, manageability, all that. So over here, we are including some of the plugins and the algorithms that Uzair talked about, and I'll talk more about it based on the time we have. So these are like, things that we would include, and how do we include that? So we came up with, and this is no new thing, it's a declarative, way of defining policies, which has been there in the software-defined network, storage, infrastructure, all that security, right? So carbon intense, energy intense. Okay, now, one thing we want to say here is our work was not so much, actually it was not about embedded carbon at all, which doesn't mean that it's not important. We can have the debate whether it's important or not, but we were focused only on the operational carbon. What that means is the carbon intensity of your actual energy. So basically, the thing that Uzair explained, right? You're moving your workload based on wherever the renewable energy is available and so on and so forth, right? So with that in mind, the carbon intense here are operator level and developer level. So we had some APIs where, for example, not just API, but like some policies, which like a XML file where we are defining, okay, for operator, it's like a system, cluster, multi-location, region, whatever way you define your infrastructure, right? So the operator will say, this is my current carbon, this is how much I need to manage. Over this period of time, I need to reduce it. Those type of intents are described there, right? And they are connected to the system. Okay, so next is developer level. What does it mean at developer level? They are talking more on the application layer. So in their case, they will say application layer, you can go all the way to the pod. So that's what we describe by kilowatt hour, kilogram, whatever the carbon for your workload and infrastructure. Okay, so moving down, the next layer in the orchestration is basically what we call the scheduler orchestrator plugin. Now, there is not a single orchestrator for systems, right? I mean, Kubernetes and all these others are quite popular and they become more or less ubiquitous. But her idea is where we come in is the scheduler plugin, mainly scheduler plugin. But there's also like things like, you can change replicas. For example, one of the examples that Uzair was showing where we say like, okay, I'm running if it is a pod and if it has like 5, current replicas. If I really don't have the need, I bring it down. I mean, that's nothing new. That's like a load-based control that you would do. But now we're doing it based on the carbon budget and so on and so forth, right? So those type of explainable plugins that we can put it in there. So that's the orchestration layer. Below that, we have our way of describing those. We call them API. You can call them capability, but they are basically how you're going to sense and control the overall system. So we thought of describing this in 3 ways, right? One is the system itself. Now, one could argue that system can include cooling, but we said that cooling will have its own control plane. Well, it does, and there are things that you can manage in the cooling side of the house separately, even though it has to all get connected, right? And the system part is really the system, which is the hardware, building the software, all the hardware features for the power, carbon, and so on and so forth. And then the third layer of API is basically what we call the facility. This is the OT kind of interface. Usually we are talking about here is the electricity part of it, right? So what is the energy? What is the carbon intensity? Okay, so there are APIs like electricity map, what time there are work in progress. But what if you had your own system and you had your own renewable energy, like solar and wind that you are creating, and you want to use that? So you will have a system where you can see what the consumption of those carbon things are, or at least their incoming energy carbon intensity. So taking this whole picture, right, and below that, I'm not going to go through all the details in the hardware because we are all familiar with that. But the main thing I want to bring here is the orchestration layer, the intents, and then the APIs, right? And then really quick on the legend. For us, this is our way of thinking, and this is why we are coming here is, there are certain things that each of these systems will do, but then there are other things that, interoperability will work and so on and so forth. So with that, let me jump into the examples of the API. So again, there are mock examples, but there are things that you can control at the temperature, at the system level. You can do like reading and writing of the things and power control and so on and so forth. And so basically, these are all the examples. I kind of went through all of that in examples. So let me just quickly move to the prototype. So very quickly, I'll go very fast on this. The way we built this is distributed systems. The first part is really the global you see on the left. If you see the most left, this is where the carbon intensity gets defined that I talked about, the operator and developer plugin. And then we kind of broke it down into 2 components, the optimization layer, which does the optimization based on the telemetry and serves the models, and then the execution layer, which actually implements those. And then you have like a regional, so multi-cluster, and then you have like a per cluster, and then you have a node level. Okay, so very quickly I don't go through all the process here, but very quickly, the cluster itself is responsible for defining what the cluster level objectives are. The multi-cluster will do optimization based on several parameters that you provide, and then it all gets served, and then it's like a distributed system that we are using. And the node agent, we are talking about it here is like a wrapper. It can use whatever the APIs are provided at the system level that we talked about on both cooling as well as the system level. So this is basically a very quick, it's very hard to go through everything in like the time we have. So this is pretty much like the prototype implementation. It's a distributed systems, one thing I want to tell you. Second thing is we broke it down in a way that you can scale from, like a few clusters to maybe hundreds and thousands of them. So again, we have not tested it with that scale, but we have emulated it with at least like a few dozen sites that we can use this type of data and then see how we can feed those algorithms. So that's what we mean in a nutshell to create an architecture and a prototype, this implementation that we have of a solution. And again, this type of solution, and this is where I will come to the call to action. This type of solution we all can build, right? But if a system has heterogeneous and it has different system parts, which are cooling, which are hardware from all the different hardware silicon providers or even the system, so this is where the API layer comes in, right? And so our call to action here is, see if we can do the infrastructure level APIs. Maybe we can have OCP drive it, the facility and the cooling level. I think there's already a lot of work, but we try to do some standardization, and then the energy or the facility API we influence. And so that's pretty much it. If you want to add anything, and I want to, the prototype I showed, basically is all the code was written by these two gentlemen, Marcin and Mario, so I want to give them the contribution for you. Anything you want to add?
No, I think so. You covered it all. So
Okay.
thank you.
Sorry for going a little fast, but yeah.
I don't know how much time we have if we want to take questions.
We're actually all out of time, but
Okay.
thank you very much.
Thank you.
Okay.